So yeah, this is backward.
Yeah.
Good. Okay, any question you have? Wake Forest, will you be able to take the test on December 2nd in the evening, like 5:30, as everybody else?
No, we're
No?
gonna have to take it probably during the day sometime.
Okay, so I will email the test to you, like not to you but to the to professor, and then you can take it whenever you decide to take it, I guess. And same thing about cones, right? You can take it at your time.
Yes, I should be able to take it that day.
Oh, in the evening, should I have the video on?
What time is that?
It's 5:30 p.m.
I guess I can make arrangements with you via email.
Okay, fine. So I don't have the room yet. Yeah, I'm trying to find a room for the test, because I think that's what you asked me. Okay, so what we were doing last time was that we assumed a quadratic form for the Helmholtz free energy is quadratic in the strain E and quadratic in the temperature change theta minus theta 0. Yes? Oh, you can't see anything. Oh, let's see. Document camera. Okay. So it works. Good. Thank you. Okay, so we expanded this Helmholtz free energy in terms of Taylor series, keeping quadratic terms, and we ended up with an expression for the second Polar-Kirchhoff stress tensor. So this is the initial stress, which we talked about. Like in some cases, you cannot get rid of the residual stress, like in a composite or in a fluid. But in metals, you can anneal the specimen and you can get rid of the initial stress. So we will assume now that initial stress is 0. Okay. Then the question came up, what is alpha hat? No, in the book, I don't have a hat there. And so my notation in the class and the book will be opposite of each other. So alpha hat is the stress temperature modulus, and the question comes, how do we find it? What is it equal to? So to find this stress temperature modulus, we look at a, say, free body. So let's say we have a free body, means you are not applying any loads to it. And we say heat it up uniformly. Raise the temperature uniformly from theta 0 to theta. So what will happen? It will expand. And the expansion will equal the coefficient of thermal expansion times the length times the temperature change. So the displacement of any point, let's assume we have taken care of the rigid body motion, so it's not going anywhere. This is the coefficient of thermal expansion. That's like change in length per unit length per degree temperature rise. So if I multiply by the coordinate of a point, so I will get the change. So you can think of, because this coordinate is from the origin, so you can think of, say, origin is fixed. And if I multiply by the change in temperature, so I should get the expansion, like how much it has increased in length. This is not quite linear expansion because alpha for a composite may or may not be a diagonal matrix. The coefficient of thermal expansion for a composite along the fiber is quite different from that transverse to the fiber. That is true for anisotropic materials. Anisotropic means the materials which are not isotropic. Okay? Isotropic means material properties are same in all directions. So anisotropic will be material properties are not same in all directions. Bone is a typical example, but for biomechanics people, the most typical example is the muscles. Our muscles are not isotropic. Okay? They are aligned in particular directions, and that is to provide strength in that direction. So they are not isotropic, and therefore coefficient of thermal expansion need not be same in all directions. That's why you see alpha A, B, and not a diagonal matrix. So what is strain then? So what will be E? So to find E, we need to find UA, comma say C, that will be alpha AB, delta BC, theta minus theta 0. And that's alpha AC, theta minus theta 0. So E, AB equal, well, twice of this equals UA comma B plus UB comma A plus say UK comma A, UK comma B. That's the definition of Green-Lagrange strain tensor. Up to here is small strains, and if you have finite strains, then this is the definition, and that's what we have been using for Green-Saint Venant strain tensor. So if we substitute this in here, we get alpha AB plus alpha BA, and that's theta minus theta 0 plus alpha KA, alpha KB, theta minus theta 0 square. Does it make sense or not? All I'm doing is substituting for the displacement gradient from this expression. Alpha is the coefficient of thermal expansion. Okay, say at this time it is like 9 numbers because it's not necessarily symmetric. So what will be then as the stress? So SAB, we found last time that SAB equals this. So CAB, NP, ENP plus alpha AB hat theta minus theta 0. So let's substitute for E. Does it make sense? So we took a free body. By free body, we mean there are no loads acting on it. And I think when we talked about Newton's first law of motion, we defined a free body. A free body is one there is no force acting on it, neither body force nor surface tractions. Okay. So what will be the stress in the free body if I uniformly heat it? What will be the stress in a free body if we uniformly heat it? Is my question making sense? Like I take a bar of steel, put it in the furnace, not that it melts, but just like put it in the furnace, say at 300 degrees centigrade. So what will be the stress in the bar?
There should be zero stress.
It should be zero stress because you are not really, it's not constrained anywhere. So I should get 0 because we have a free body. So 0 should equal then CAB NP, and ENP is this quantity, so that's alpha np plus alpha pn theta minus theta 0 plus alpha kn alpha kp theta minus theta 0 square plus alpha a b hat theta minus theta 0. So this equation should be valid for all values of theta minus theta 0. This equation should be valid for all values of theta minus theta 0. And therefore we can get alpha hat. So alpha hat AB equals CAB NP alpha NP plus alpha PN plus alpha Kn alpha Kp theta minus theta 0. Because you can divide by theta minus theta 0. Oh, minus sign. It's minus sign, right? I think you said bracket.
Shouldn't all of that be multiplied by CAB?
Oh, yeah. Yes. You are right. Yes, all of that should be multiplied by CAB. Yes, thanks. Yes, Franz.
Why didn't we put in a 1/2 when we put in the EAB?
Oh, I did not put that 1/2 either. So that's another problem. So I should put, let's see, where should it go? It should go here. Yes, you are right. Okay. Now, generally we assume alpha is symmetric. It's an assumption. There is no reason for it yet, or I cannot really give you any reason. So if alpha is symmetric, yes.
Why? Why is just that one term divided by 2 and not the other?
Not the other one. Probably the other one should be 2. Yeah. Yes, the other one should be also. So if alpha is symmetric, that's an assumption now. If we assume that alpha is symmetric, so alpha NP equals alpha PN, that's an assumption. That means we have now 6 coefficients of thermal expansion rather than 9. If alpha is symmetric, then we will have 6 coefficients of thermal expansion rather than 9. Typically, the value of coefficient of thermal expansion typically is of the order of 10 to the power minus 5 or minus 6 centimeter per centimeter per degree C. Typically, it's 10 to the minus 5, 10 to the minus 6 of that order of magnitude. I think some of you probably, Jessica, you might have measured it, I don't know, for a coefficient of thermal expansion for a fiber, say. Okay. It's typically in the range of 10 to the minus 5 or 10 to the minus 6 centimeter per centimeter or meter per degree C or per degree Kelvin. If you say Fahrenheit, then you have to divide by 1.8, but we are talking about order of magnitude, we are not giving the exact value. So if this is true, if it is of the order of 10 to the minus 6, what will be the magnitude of this term? So 10 to the minus 12. And this one is 10 to the minus 6. we are not going to raise the temperature by a million. Right? Actually, our theory is not applicable. Our theory is applicable only when theta is slightly different from theta 0, because we expanded things in terms of Taylor series and kept quadratic terms. So our theory is not applicable if you change the temperature by a lot. So we can neglect this term. So we can say then that alpha AB hat is nearly equal to minus CAB NP alpha NP. So if you know the Young's modulus, and if you multiply that by the coefficient of thermal expansion, then you get this stress temperature modulus. So the value of the stress temperature modulus is not small, because Young's modulus is pretty big. It's in GPAs. So if the Young's modulus is in GPA, which means like 10 to the power, 9 pascals, and this is 10 to the power minus 6 pascals. So we are talking about like kilopascals per degree Celsius. So alpha hat as the magnitude of kilopascals per degree Celsius. So if you raise the temperature by 100 degrees, you are going to induce a stress of roughly 1/10 of a megapascal, which is not very large. It depends upon the material, of course. Right? But if you have a carbon nanotube, then C, Young's modulus for a carbon nanotube is a terapascal, roughly. So that will mean 10 to the power 12. And if you, I don't know the coefficient of thermal expansion for a carbon nanotube, but let's assume it is the same as that for a carbon fiber. Then we are talking about 10 to the power 12 times 10 to the minus 6. So we are talking about megapascals per degree Celsius. So you can induce significant stresses in a carbon nanotube if you raise the temperature by a few degrees. So there's a talk, there's a proposal, people are thinking or dreaming that we can put some medicine on carbon nanotube and we can treat it with some enzymes so that if I swallow it, or if a human being swallows it, then somehow it is directed towards the right place in the organ, say for cancer treatment. If you drink hot coffee immediately after swallowing the carbon nanotube, you may induce considerable stresses in it. Well, that's what it says here, right? Because nanotube is not freely is floating around in the body now. When once it is in the body, it is surrounded by tissue. So, and the coefficient of thermal expansion of the tissue and the nanotube may be different. Of course, Young's modulus is totally different. So there can be. I'm not saying there will be. Will be is different from can be. Okay, so the next question is then, what is the entropy? So when we go back to this expansion we had of the free energy, Helmholtz free energy, and what is entropy in terms of Helmholtz free energy. So the entropy inequality said that eta, that's the specific entropy or entropy per unit mass. Oh, there are two quantities in the literature I think we should be careful about. One is called something per unit mass, and other is something per unit volume. So if you measure something per unit volume, then that's density. Like mass density is mass per unit volume. If you measure something per unit mass, then that is specific. So this is specific entropy, because this is being measured per unit mass. and we found this was minus delta phi over delta theta. So rho 0 eta, because we expanded this in terms of rho 0. So if I differentiate, I get A, that's the first term, and then I will get B, theta minus theta 0, and we will get plus alpha L m hat EL. And oh, everything, yeah, it's negative. You are right. So I goofed. So let me put minus here and minus here. Then I can. It's the same thing. When I. Okay, now let's simplify the expression we had. We had phi equal to E minus eta theta. But I'm headed towards the following. We know the balance of internal energy. So that's where I'm headed. So I'm going to get an equation for the temperature. Balance of internal energy says rho 0 E dot equals minus QL comma L plus TIL F dot IL plus rho 0 R. That's the balance of internal energy. We derived this, I don't know, some time ago. No, probably 3 weeks ago. So I'm going to substitute for A dot here from this one and this one. That's where I'm headed. And that will give us the equation for temperature. So if we take this and differentiate it, so we get phi dot, which is really delta phi over delta theta, theta dot, plus delta phi over delta FIL, F dot IL equals E dot minus eta theta dot minus eta dot theta by the chain rule. But this term cancels with that. Therefore, E dot equals theta eta dot plus, this is TIL over rho 0 FIL dot. Delta phi over delta, this quantity is the first Kirchhoff stress tensor. That again was given by entropy inequality, except that rho 0 times this was first Kirchhoff stress tensor, so that's why we are dividing by rho 0 here. Is it okay? Therefore, rho 0 E dot equal rho 0 theta eta dot plus TIL F dot IL. And now I substitute in this equation. So what do we get? So I have rho 0 theta eta dot is right here, and actually I have for rho 0 eta dot, rho 0 eta. So let me scratch this. So I have theta.
Can I ask a question real quick
Yeah,
before
sure.
you go forward? So I think when you were writing the line up earlier, you said that the TIL was the first peel of Kirchhoff,
Right.
and so is it okay? Never mind.
I think we derived
Yeah.
TIL equal rho 0 delta phi over delta FIL. The entropy inequality gave us this relation.
Okay, then I guess I'm
You're confused.
confused about when from before. I guess when you've been writing the first peel of Kirchhoff, you've always been
Oh.
so the overtop, and so
Yeah. My notation is bad. Yeah.
Okay.
Yeah. Sorry. I think I'm. Well, no excuse. It's my mistake. Yes. Yeah. I should have a tilde on it. Yes. Yeah. Thank you. It's my mistake. Yes. I should have a tilde on it. Okay. Yes, you are right. Okay, so now let's substitute for E dot, this quantity. So we get theta rho 0 eta dot. So let's differentiate this. A is a constant, so its time derivative is 0. So we get B theta dot. And now I need to be careful about my signs. So I should have a minus B here. And minus alpha LM at ELM dot. Okay, plus TIL tilde F dot IL should equal minus QL comma L plus TIL tilde F dot IL plus rho 0 R. And now we are in business, I think. So we are getting the heat equation now, and that's the goal. So this term cancels with this one. So what we get then is, if you change the sign, well, let's say minus B theta dot equals minus QL comma L plus rho 0 R plus alpha LM hat theta ELM dot. The reason I still have minus B is because B is going to be a negative quantity. And I of course, if I had put minus B, when I expanded this in terms of Taylor series, if I had put minus B here, then I would have gotten a plus B here. So that's where but anyway, our algebra is correct if we, So this is the equation that gives us the rate of change of temperature, theta dot. When you are not quite used to it, well, first of all, let's look at QL, which we have not simplified yet. And what is the what is this term coming from? Or what is the meaning of this term? R is the supply of energy because of radiation, like you are sitting in the sun. So R is the energy you are receiving per unit mass from the sun, or from bodies which are not touching you. Q is the energy you are receiving from bodies that are touching you, like heat conduction. This term is the working, that means rate of work done due to thermal stresses. Alpha is the stress temperature modulus. If you multiply it by temperature, you will get stress. And if you dotted with E dot, you will get the working. So what you really get is alpha LM hat theta, you get a second Piola-Kirchhoff stress tensor, because that was the way, that's the way we derived it. So you see, second Piola-Kirchhoff stress tensor is related to alpha hat times the temperature change. So this quantity alpha hat theta is the second Piola-Kirchhoff stress tensor. It's dotted with E dot. Dotted means taking this inner product or scalar product in vectors of 6-dimensional space. Okay, now what about the heat flux? Yes.
Is there some sort of convection term?
Convection? That will come in through the boundary conditions. See, convection, like, I think it's a good question. In summer, when we get hot, we sit in front of a fan, and that's to cool ourselves off. So what is happening is the fan is blowing air on us, and that air is extracting heat from the surface of the body. So that will come through the boundary condition. Also, one can receive heat through the surface. Like I can cover myself, or I can wear dark clothes. And if I wear dark clothes on a sunny day, the coefficient of absorption of those dark clothes, generally speaking black clothes, is much higher than that of white clothes. So you wear, if you want to receive more heat from the sun on a sunny day, wear black clothes and sit in the sun. Then you will feel warmer than if you wear white clothes. Of course, you can wear aluminum foil that will reflect waves, then you won't feel much energy. So it's all up to you. Okay, now what about the heat flux, QL? So we said Q is also a function of E and theta and G, with the condition that the entropy inequality says that if the temperature gradient is 0, then the heat flux is 0. If the temperature gradient is 0, then the heat flux must be 0. That was what we derived from the entropy inequality. We cannot have a heat flux in the absence of temperature gradient. So we expand this in terms of Taylor series, same way as we did for the free energy. We expand heat flux in terms of Taylor series. The only difference is we are going to keep terms linear. We are going to keep terms of first order in the temperature change and first order in the temperature gradient change. So we get QL of E, theta, and G equals QL. There is nothing here. E is 0 in the reference configuration, theta is theta 0, G is G 0. So that's the first term in the Taylor series. And if we take the next one, we are going to expand in terms of, say, E now. So we will get plus or minus is your choice. So this is ALMN, EMN. Say plus. It's common convention to put minus here. So it's KLM GM minus GM0. So that's expanding in terms of G. And then let's expand in terms of temperature change. So that's BL theta minus theta 0. And remember now, A, K, and B, these three quantities, they are evaluated in the reference configuration, so they are constants now. A is a third order, like it has three indices. K has two indices, B has one index. So K is called thermal conductivity. I think we have said that before. So K is the thermal conductivity tensor because it has two indices now. So now we need to satisfy this constraint. Entropy inequality cannot be violated. The second law of thermodynamics cannot be violated. So if I set heat flux equal to 0, that means this term is 0. So these two must be 0 then. See, if there is no heat flux, if there is no temperature gradient, I should not get any heat flux. But these two terms don't have any temperature gradient in them. So this A then must be 0 and B must be 0. There is no, yes, Katie, go ahead.
I'm sorry, I
No,
didn't
it's
hear.
okay.
What are A and B equal to?
It's a good point. So BL is delta QL over delta theta evaluated at E is 0, theta is theta 0, G is G 0.
And what's A equal to? And what do these mean, like, in a real sense?
In the real sense, actually, what it says is how much heat flux will you get if you strain the body? How much heat flux will you get if you change the temperature of the body? So B means how much heat flux will you get if you change the temperature of the body. A means how much heat flux we will get if you strain the body. And the answer is 0 because entropy inequality says you cannot get heat flux unless you change the temperature gradient. But math requires that I expand this in terms of Taylor series, and that's what I did because we have 3 variables here, so we will get 3 terms. Q is a function of 3 variables, E, theta, and G. So if you expand in terms of Taylor series, you will get 3 terms. And we are not keeping the higher order term. The higher order term will be like E square, G square, theta square, and then cross multiply. And the reason we are not keeping the higher order terms is because in our stress strain law, we have only terms which are linear in E and linear in theta minus theta 0. So it's not fair. It's not a fair game to keep linear terms in the stress strain law and keep higher order terms in the heat flux, unless you are really in a space shuttle and facing the sun. Then the heat flux is very high. So you will get a better approximation if you keep higher order terms. However, for things that we are considering now, we are saying change in temperature is not very high, relative change in temperature is not very high, but if you are very close to the sun, like if you are in space 50-60 miles from Earth, the amount of radiation you are receiving that you mentioned from the sun is pretty high, and that's why on the space shuttle you have ceramic tiles on the outer surface so that the material can withstand high temperatures. It doesn't melt. If you had steel or aluminum, it might melt, and then our colleagues will not be able to come back. Okay, so that's why we use ceramic tiles on the outer surface so that it can withstand the high temperature. Does that help? Okay, so this A is 0 because of the because when you set G equal to 0, you should get heat flux as 0. This has no G term. This has no G term. So now if we assume that the bodies in the reference configuration, the body is at a uniform temperature. So if the body is at a uniform temperature in the reference configuration, then there is no temperature gradient in the reference configuration. So what will happen to this term? So if there is no temperature gradient, what will happen to this term? Well, here is the rule. No temperature gradient, no heat flux. So Q in the reference configuration will be 0 too. So from now onwards, we are going to say that our reference configuration, the stress is 0 and temperature is uniform. So in the reference configuration, the stress is 0, so there is no residual stress, and Fred is out of business because he is testing composites, and there is no way he can achieve that. There is no way in a composite you can have zero residual stress. But you can have uniform temperature. So if we make these two assumptions, then what we get is that SAB is CAB, NP, ENP, and plus alpha hat AB, theta minus theta 0, and QL is minus KLM GM, which is same thing as KLM theta comma M. So it's the temperature gradient with respect to coordinates in the undeformed state. K is the thermal conductivity. We are dealing with anisotropic bodies. Material properties are directional dependent. Material properties are directional dependent. Okay, so now, so with this, what are our balance laws? So first thing we get from this equation then is minus B theta dot equals K L M theta comma M comma L plus rho 0 R plus alpha L M hat theta E dot. This is E dot. Now I don't know. It's nothing to do with L. This L. Maybe I should put this way. This goes here. It's E dot LM. I think what you probably have come across before is heat conduction in a rigid body. In that case, we have denoted this term evaluated in the reference configuration at the reference temperature. So this is specific heat. Minus B times the theta is specific heat. K is thermal conductivity, which I think you have seen before. Most of the time you take radiation R term to be 0. And if the body is rigid, there is no strain. So E dot is 0. So you get the classical heat equation. Now you get specific heat times rate of change of temperature equals the divergence of the heat flux. So this is the equation for temperature, except we have a coupling now, because E depends upon displacements. So if the body can deform, then E depends upon displacement. What about the equilibrium stress equation, like conservation of linear momentum? So we wrote rho 0 ui double dot, which is the acceleration. And this time I will remember, so Francis does not have to correct me. I will put tilde on it. Plus rho 0 pi. Yeah, I'm sorry, I forgot those tilde. I should remember those. And when I realize if you make a mistake, you lose a point, but if I'm making a mistake, I don't lose anything. Except on my teaching evaluation, you can write something. Okay, so what is TIL? TIL tilde is FIMSML. Because we defined S as F inverse T tilde. We defined S as F inverse T tilde. So, and what is F? F is delta IM plus UIM SML. F is displacement, F is deformation gradient. It's delta little xi over delta big X, which is equal to Kronecker delta plus, we denoted this by H, or it's a displacement gradient. Because now we are writing everything in terms of displacements. Okay, so if you agree with that, then we have delta IM plus UI comma M. Now we need to substitute for S. And S is this quantity. But now we are taking SAB0 to be 0. So it's C M L N P times ENP plus alpha hat ML theta minus theta 0. So this bracket closed, and then the outer bracket closed, comma L plus rho 0 BL. And I think this time I was awake. So at Ti tilde is this quantity. So the first term I copied here. Then for S, I copied these two terms. They are right here. Sorry, Fred, is it okay? So those S is here, and then you take the divergence, which means differentiate with respect to L, plus rho 0 pi. So these give us these two equations. If you want to solve a thermoelasticity problem, if you want to solve a problem, a coupled thermomechanical problem, a coupled thermomechanical problem, then these are the two equations we need to solve. These are the four equations actually. For I equal to 1, 2, and 3. So we have three equations in displacements and one for temperature. So how many unknowns do we have? In a thermomechanical problem, Katie is thinking, so she's going to tell us. How many unknowns do we have in a thermomechanical problem? You know what I mean by thermomechanical or thermoelastic problem? Thermo means temperature. Elastic means a elastic body. So how many unknowns do we have in a thermoelastic body? Kim, Jessica, Catherine at Wake Forest will help us. Catherine?
9. I have
How
no
did you get
idea.
Oh, you have no idea.
It's gotta be 4.
It's got to be 4. See, it is 4. There are 3 components of displacement. There are 3 components of displacement. That's all we have been studying for the last 15 weeks, that a continuous body has 3 components of displacement. And now it has also temperature, because we are saying thermoelastic. So to find the deformed state of a body, we have to find 4 things. Displacement of each point, 3 components of displacement, and 1 temperature now. So if you are solving a mechanical problem, purely mechanical problem, then we have 3 components of displacement. If you are solving a coupled thermomechanical problem, then we have 4. If you are solving an electromechanical problem, which we have not talked about, then you need electrical potential. So you again will have 4. If you have thermo-electromechanical problem, then you have electric potential, temperature, and 3 components of displacement. But then we need 1 more equation. How many equations do we have here? I will quit. I realize I'm 2 minutes over time. So, but how many equations are in this box I put in? Hey, I mean, you are tired, right? But
4?
very good, 4. This is a scalar equation for temperature. There are 3 equations here for I equal to 1, 2, and 3. So there are 3 equations here. So we have 4 equations for 4 unknowns. Are these equations linear? Are these equations linear? The answer is yes or no. They are not N-O-T not. They are not linear. The ones we have derived are not linear, because you can see theta multiplying with E. E is displacement. E has displacements in it. E itself is quadratic in displacements. And you see E here multiplying with U. So these equations are not linear. These equations account for large strains. Strain can be very large. You can pull my skin. This is considered. However, the stress-strain relation is linear. So stress is a linear function of finite strains. Okay, so I will see you tomorrow. And thank you. So I think we have only 1 more class to make up. Yeah, thank you for letting me make up the class. You probably would have been happier if we didn't make it up.
You going to the training?
I didn't try it.
You said you were going.
Yeah, I don't
No.
Next homework is on Friday.
Or you can just give me tomorrow.
Tomorrow.
Otherwise, I have to carry it home and then bring it back. I think it's due tomorrow, right?
But due on the first.
Just give me on first then.
Okay.
That way, it's not that I will lose it. But if you give me today, then I have to carry it home and bring it back. So I'll rather you carry it.
When is everybody meeting? Okay. Oh no, I'm on campus right now. I just got out of class.
Okay, well, you guys do that later. I'll do that later.
Yeah, I couldn't decide whether to go.
Okay.
Because I'm gonna go grab dinner on campus after here, but then I realized it might be like 7:30 by the time I get to campus. No, I guess I'm doing good. Okay, well then I'll go ahead and grab some food. And then if we're studying at your place, I can just walk there, but
Hey,
if
Paul,
everybody's
what's up?
studying at Brian's, would you mind like swinging by and grabbing me? So
I
awesome.
really do, but, I need to get a lot done before Friday. I really can't.
Yeah, that sounds good, because, yeah, dinner shouldn't take that long.
But I'm gonna bring my games home over.
So I can eat before 7:30. Okay, great. Just give me a call, I'll bring those. Alright, bye.
Okay, well, thanks, there you go. Sure. Yeah.
Alright, I'm good for dinner,
Okay,
if you are. I just need to go get my stuff now,
good, what's that?
my vibration stuff from yours. So that way, because Max may pick me up from campus, so.
I'm gonna drop over back.